Listen up, brothers. I've pulled you in today because we have a potential crisis on our hands, and I need your absolute, undivided attention. I've put together this explainer covering our official emergency protocol for high SVI and poor sludge settling. I need you to understand exactly what is at stake here. You know, when the plant is running smoothly, it's really easy to get complacent. But process collapse is an absolute beast, and if we don't catch the signs early, we literally lose the plant. So I'm going to walk you through exactly what I expect from you, step by step. Stay with me. Here's our roadmap for today. First, we'll cover the sludge emergency. Second, diagnosing the root cause. Third, the investigation protocol. Fourth, our rapid response solutions. And fifth, the checklist and final lessons. Let's dive right in. Section 1, the sludge emergency. Process collapse in 24 to 72 hours. Brothers, I need you to respect the ticking clock. If you notice poor settling out there and you do not act immediately, I guarantee you the whole system drops in exactly 24 to 72 hours. We don't have days to figure this out. We only have hours. If you fail to act, here is the domino effect. First, we're going to see a massive 3 to 10 times spike in total suspended solids right in the effluent. Next, because that sludge is overflowing, our MLSS drops in the aeration tank. And listen, when we lose that sludge, we lose our ability to treat organics. The sludge retention time gets completely disrupted, causing severe microbial shock. And the operational costs, they skyrocket, because I'm going to have to authorize emergency polymer and chlorine. So I want you doing your rounds on the floor with your eyes wide open. These are the visual symptoms I need you looking for. Suspended sludge in the secondary clarifier with absolutely no clear interface. A sludge blanket that barely even moves. Rising clumps of sludge just bubbling up to the surface. And a supernatant layer that looks cloudy, pale brown, or kind of gray. If you see this, you don't wait, you call it in immediately. Moving to Section 2, diagnosing the root cause, identifying the exact enemy. Look, we can't fight the problem until we know exactly which type of sludge failure is actually happening. I need you working closely with the lab to identify our specific enemy. You gotta know the profile. First, sludge bulking. That's caused by filamentous bacteria, and it shows up as a stretched out network under the microscope. Rising sludge happens when nitrates break down anaerobically. You're gonna see nitrogen gas bubbles physically stuck to the flocks. Pinpoint flock? That just means your sludge is too old, breaking apart into tiny fragments under 50 microns. And finally, dispersed growth. That means a toxic shock just killed off our microbes, leaving single, dead cells just floating around. Section 3. The investigation protocol. These are your step-by-step diagnostic actions. When that alarm sounds, I expect methodical, precise action. The shift leader must assign these diagnostic steps right then and there. No guessing, brothers. Just measuring. Here are the 4 critical steps. Step 1. The lab measures the sludge volume index, your SVI30 and DSVI. Step 2. Get that sample under the microscope to check the filament index. Step 3. Operations needs to check the dissolved oxygen in all zones of the aeration tank. Step 4. Engineering analyzes the food-to-microorganism ratio and the return-activated sludge flow. I need every brother out there doing exactly what they're assigned to do. Now this number right here, it's totally non-negotiable. Dissolved oxygen must be at least 2.0 milligrams per liter everywhere in the aeration tank. If you let it drop, I promise you, filamentous bacteria will absolutely choke out the good biology. You have to keep that air flowing. And if the lab tells you the SVI30 is over 150 milliliters per gram, well, we've crossed the severe threshold. This means we have critical bulking on our hands. It requires my immediate intervention, and it requires you to execute the rapid response solutions without hesitation. Which brings us to Section 4, Rapid Response Solutions, Action Plans for the first 4 to 48 hours. Brothers, once we have the diagnosis, we move straight to action. We're executing the emergency plans to save this plant. If we're dealing with filamentous bulking, here is your aggressive response. In the first 0 to 4 hours, you increase the RAS flow to 120 to 150% of the design value, and you reduce the incoming load. Simple as that. Between 4 and 48 hours, the physical chemistry engineer is going to chlorinate the RAS. But pay attention, the dose is strictly 2 to 5 kilograms of chlorine per 1,000 kilograms of MLSS per day. You must monitor the ORP. We want to trim those filaments, not kill our useful microbes, all right? If the problem is rising sludge, I need you to stop that anaerobic denitrification in the clarifier. You do this by increasing the waste-activated sludge by 30 to 50% just to get the sludge moving faster. Do not let that sludge sit for more than 2 hours. We must starve out the nitrates, keeping them well under 5 milligrams per liter, and optimize our anoxic to oxic ratio. Now, what if it's pinpoint flock? Well, your sludge is simply too old. So I'm directing the operators to aggressively spike the WAS to 150% of the normal dose for 2 to 3 days. You have got to waste out that old sludge. Maintain DO strictly between 2 and 3 milligrams per liter and rebalance your food to microorganism ratio. If dispersed growth tells us we've got a toxic shock, your very first move is immediate isolation. Close those valves. Send the inflow straight to the equalization tank. The lab has to test for heavy metals and cyanide. We neutralize the toxins. And listen to me, only after the water is 100% safe will we even think about reseeding. When we do, we'll bring in 20 to 30% new sludge from a neighboring plant. Sometimes it's just a physical hydraulic overload. If that's the case, you bypass to reduce the flow into the clarifier. You can absolutely add 3 to 5 milligrams per liter of polymer to force the settling. But brothers, hear me loud and clear on this. Adding polymer is only a temporary bridge. It is not a permanent fix. You still have to check those surface overflow rates. Section 5. Checklist and final lessons. This is the shift leader's ultimate protocol. All right, this is what brings the whole shebang together. Before any shift leader hands over this plant to the next crew, I require a mandatory checklist to be completed. Let me run through these non-negotiable metrics for you. SVI 30 must be below 150. I want the RAS flowing between 50 and 100% of design. DO has to be strictly 2.0 or higher everywhere. The pH needs to be steady between 6.5 and 8.5. And you better make sure you have enough polymer stock to run for 48 straight hours. Every single one of these boxes must be checked before you can declare the crisis officially averted. I'm going to leave you with this final thought. Prevention through the tight monitoring of your DO, your FMM ratio, and your SRT is always cheaper and a whole lot less painful than a 72-hour disaster recovery. So I have to ask you, are you going to be the shift that lets a collapse happen on your watch, or the shift that catches it early and holds the line? Brothers, strict daily monitoring is always our best defense. I am counting on you. Watch the gauges, trust the protocol, and keep this plant running. Dismissed.